Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London in the UK, and this is a new episode of the podcast Turbulence at the Exascale. If you're not familiar with the podcast, we are trying to gather the view of the scientific community regarding exascale computing for turbulence research, and we are interested in better identifying the challenges and opportunities that will come with exascale computing. So this podcast is part of the ExCALIBUR initiative, which is a big project here in the UK led by the Met Office, the UK Atomic Energy Authority and the UK Research Innovation, and its aim is to deliver research and innovative algorithm developments to harness the power of exascale computing. So there are currently several working groups working on the ExCALIBUR project, trying to identify user cases, and I'm leading the one on turbulence, and this is why we are here today. So today I'm very pleased to say that we have another guest from EPCC called Mark Bull, and he's an expert in benchmarking, parallel algorithm, parallel programming APIs, and use of course, high performance computing, and he's also involved in a master degree at Edinburgh. So we are going to discuss about this, how we can teach high performance computing to students. So good morning, Mark.
Good morning, Sylvain. Very happy to be here.
Likewise here. So we are going to crack on with the questions. So for those who don't know you very well, it would be good if you could tell us more about yourself, where you are from, what you have studied, and also how did you end up at EPCC?
Sure. So I was actually born in Scotland, but I grew up in a variety of different places in the UK. I did my first degree at Cambridge in maths, and very quickly realized I was not cut out to be a career mathematician. And so after I'd finished that, I went and worked for the Met Office for a couple of years when it was still in Bracknell. And then I decided that I did want to go back into academia, and I went to Manchester University to do a master's in numerical analysis. And then I ended up staying in Manchester, working in computer science department in parallel computing, and doing my PhD part-time while I was there. And then in 1998, I moved up to EPCC in Edinburgh, and I've been here ever since.
Fantastic. So you said you started your studies with mathematics, but now you're more a high performance computing expert. So how did you become interested in high performance computing?
So really, I was a bit of a latecomer to computers. I didn't really learn to program until I was working at the Met Office. And even then, it didn't really grab me that much. But my interest was really sparked by my master's dissertation project, which involved parallel programming. And at that point, I just thought, oh, wow, this is amazing. Parallelism is just so much more interesting and challenging and fascinating than sequential programming. And that's what really got me hooked into it.
Fantastic. So you have been working, well, at EPCC for quite some time now, and I want to ask you, what's the best thing about your current position? What do you really like about your job?
I think it's probably the variety and choice of the different projects that we get to work on in EPCC, which is fantastic. And also, I think the direct contacts that we have with the scientists who are using HPC, it's really very valuable. It's interesting in its own right to be working with scientists, but it's also very valuable to motivate our research so that we are really working on problems that are of use to end users. There's also a lot of, there's a lot of us at EPCC, and there's a lot of colleagues doing a really wide range of interesting work. So there's always a lot of expertise to draw on, and interesting conversations to be had with other people here. And I also really appreciate the culture at EPCC. I think, say, it's an unusual department in the sense that it's within the university, but it's not a normal academic department. And I think the way that we manage EPCC, we've really largely avoided the kind of sort of turf wars and dysfunctional politics that can sometimes infect traditional academic departments. So from that point of view, it's a really nice place to work.
Great. So I'm going to start, before talking about your research, actually, I'd like to talk about your teaching activities in relation to the master degree on high performance computing. So, I mean, this is quite a unique degree in the UK. So can you tell us more about, well, what you are teaching within this degree and how this degree is managed?
Sure. So the degree as a whole covers a range of topics. So parallel algorithms and design patterns, and then parallel programming languages, some HPC architecture, also quite a focus on software engineering, code optimization as well. We also have a variant of the degree, which is high performance computing with data science, and there's a lot of overlap between the two programs, but the data science variant has more of a focus on data management and data analytics.
Great. Then,
personally, yeah, I mostly teach multi-threaded programming, so OpenMP and other multi-threaded models, so like C++ threads, and also some of the hardware architecture stuff. So that's my role.
I wanted to ask you, I don't know if you have the numbers, but I was curious how many students are applying every year and how many students do you take every year, or roughly?
So it fluctuates a lot from one year to the next, but I think we have probably somewhere in the region of 150 to 200 applicants per year, something like that. And we take between 30 and 70. It does vary a fair bit from one year to the next.
Great, thank you. So it's quite a large cohort of students. And sorry, I maybe this is too difficult to answer. I was wondering, do you know where those students after graduating, where do they end up? Are they going straight to industry, or some of them are staying in academia? Do you have an idea of? I guess it's
a real mixture. Yes. So some stay in academia, so go on to work in science departments, doing high performance computing in various different scientific fields. Some go into industry. Some go on to do further studies, obviously, to do PhDs in various places, and some go more into the kind of systems, high performance computing administration type roles. Okay. Yeah.
Yeah. Thank you. Thank you very much. I have another question. I think you are part of the OpenMP Architecture Review Board, and it would be good for the people who are listening to this podcast to know what do you do in this review board, and what's your role, and yeah, it will be interesting to know that.
Okay, so it's a bit of a strange name, but the Architecture Review Board is just the body that administers the OpenMP specification. Okay, so it's the place that the specification gets developed and ratified and so on. So, EPCC has been a member of this organization for quite a long time now. We joined back in about 2000, 2001 sometime. And we were one of the first sort of non-vendor or large US lab organizations to join up. But now there's a lot more HPC centers involved in OpenMP, and the membership is about 30 odd different organizations who contribute to the architecture review board. And the main work is obviously working on the specification, developing the new versions of the specification. I was actually the chief editor for a couple of versions of OpenMP, so 2.5 and 3.0. But I guess I've taken a little bit more of a backseat role in recent years, but you know, still acting to put some work in on the specification development.
So when is going to be the next big release of OpenMP? Or can you tell us what's going to be the next big changes?
So we've really just kind of gone through so 5.1 is out now.
Yeah.
So that was a relatively, as you might guess, that was a relatively small increment on 5.0, which was a fairly a reasonably big change. And I guess the big focus on 5.0 was really on a lot of the accelerator offloading capability in OpenMP. I mean, it came in 4.0, but it evolved quite a lot in. There was quite a lot of additional material in there in 5.0. So we're now really kind of thinking about, you know, what next and where to go and working towards 6.0, but that's some way off now.
Great, thank you very much. Right, let's talk about more about your research or your software development activities, and also talk about exascale computing. So can you tell us about the few projects you are working on at the moment? What are you doing on a daily basis these days?
Okay, so I guess the main project I'm working on is called LowSync, which is a sub-project of the European PRACE initiative. And what I'm doing there is it's essentially a programming models project, and we're working in collaboration with Barcelona Supercomputing Center. Mm-hmm. And what we're looking at is combining task-based programming with traditional message passing. So the idea here is that in order to minimize the amount of synchronization and unnecessary ordering constraints in applications, what you would like to do is be able to express a data flow type implementation of your parallel program. So you turn your program into a set of computational tasks, and the programmer specifies the dependencies between them. That's a nice model. It's very, very difficult to implement that model across distributed memory. People have tried to do it, but there hasn't really been a great deal of success. It's really, really difficult to make that kind of runtime scale to very large systems. So what we're looking at is basically running the task-based model inside a node, but then continuing to communicate between nodes using traditional message passing like MPI. And in order to get that to really work well, you want to be able to express your communication as tasks as well as your computation. And that requires some modifications to the runtime and to the MPI library to be able to handle that efficiently and correctly. So we have an implementation in collaboration with BSC. We have an implementation, and we're experimenting with that with a variety of different mini apps and small application codes. And we're getting some really nice results on that.
Great, thank you very much. Well, we are talking a lot about exascale computing, and I wanted to have your opinion on what do you think are going to be the main challenges if we want to make use of exascale computer efficiently. What's your view on that?
Okay, I think the big challenge is that the main route that hardware is taking to get higher performance is basically just more parallelism. That seems to be the only route left to extracting more performance from the hardware, is just to put more and more cores on the chip. And that's a real challenge for the applications, because that means that they have to explicitly express and manage more and more parallelism. So it's not something that really the compiler or the system software can handle very well at all. It's really down to the application to expose all that additional parallelism to make the application scale to more and more cores. And that means that you have to, in the application, you have to really work hard to make everything parallel and avoid even the tiniest sequential bottlenecks, because they will start to count once you get to tens or hundreds of thousands of cores.
Right, and from what you can see at EPCC, do you think the community in the UK is ready to harness the power of exascale computing, or you will say that there is still a lot of work to be done on the various applications that you see at EPCC?
I think it's something of a mixed picture. Some codes have clearly done a lot of work to try and improve the scalability, but others, often for very good reasons, will struggle to get there. And it's not always just down to the application code. There are sometimes constraints that come from the actual use cases as to how much inherent parallelism there is in the use cases. So, for example, on Archer and Archer 2, we run a lot of material science codes, and the amount of parallelism is then often constrained by the size of the molecular system that's being simulated. So no matter how, you may be working with a code that's in principle able to scale to very large numbers of cores, provided that the system that you're simulating is big enough, but that's maybe not what the scientists are actually interested in doing. So there are constraints from the actual science on the amount of parallelism, as well as from the codes. I think it's going to be interesting to see how Archer 2 gets used, because essentially, compared with Archer, we've got about 6 times the number of cores in Archer 2. But the power of each core is roughly comparable. Okay, so the computational capability of each core hasn't really changed very much. There's some slight differences, but essentially the power of a core has not really increased very much. So to see what scientists do, will they really run with 6 times? Will they really run their simulations with 6 times as many cores? Or will they really just run 6 times as many jobs, just make use of the capacity of the machine rather than the capability? Of course, I expect the truth will be somewhere in between, but it'll be interesting to see how the usage of these very big systems evolves, and how many applications are really able to run on significant fractions of the system.
Great, thank you very much. And so from your perspective, if you could change one thing in high performance computing, so it could be hardware, more memory, more bandwidth, whatever, what would you change so that more application could be used efficiently at large scale?
So I think for sure memory bandwidth is a real challenge. For a lot of HPC applications are essentially limited by memory bandwidth, and which is why a lot of them only really exploit a small fraction of the peak floating point capability of processors. I think there's some cause for optimism there. Some of the new memory technologies that are coming and these high bandwidth memory implementations should go hopefully some way to address that. So I think there is some hope there. I think in an ideal world, it would be nice if we hadn't become so heavily reliant on commodity processors in HPC. And I would include GPUs in that as well. But obviously this is dictated by the economics. Building custom hardware is no longer for the HPC market is no longer an economically viable route. But I think what that's meant is that there's limited scope for innovation in the architecture for it to be really targeted at HPC applications. We really just have to make the best of what we're given from the large volume commodity processor world. Having said that, I think it'd also be nice if hardware designers were a bit less concerned about peak performance and a bit more concerned about how easy the hardware is to program. So as processors are trying to squeeze more, the last drops of performance out of the silicon, then it's possible to improve the peak performance, but it's less clear how easy it is for applications to actually realize any of that potential.
Great. I have a couple more questions. One question is, can you tell us more about Ipragel? Don't know if I pronounce it properly, but
yeah, sure. Ipragel is something that one of my PhD students has been working on. It's a framework for graph computation, and it's inspired by Google's Ipragel framework. You can really think of this, it's a bit like a domain-specific language for graph computations. And it's what's called a vertex-centric model. So the idea is that the programmer essentially just writes the code that will be executed on each vertex of the graph. It's kind of got an iterative model, so you execute the same code on every vertex at every time step. And then you also specify how the vertices interact with their neighbors in the graph. But all the details of the optimization and parallel implementation are abstracted away from the programmer. All that's taken care of inside the framework. So really what we're trying to do is to see how close we can get to handcrafted code without sacrificing these nice programmability properties of this framework. And at the performance on very large graphs in non-volatile memory. So we have a test system at EPCC with large amounts of Intel Octane memory. So we're currently working on that and seeing how far we can extend the size of the graph that we're able to process on NVRAM.
Good, thank you very much. I have one last question. So these days we talk a lot about exascale computing, but I wanted to have your views on what do you think will come next, and in particular, I mean, do you think we are still going to have an incremental evolution of the hardware with more powerful, more energy efficient CPUs, GPUs, or do you think something big is going to happen, like a big new type of hardware. What's your view on that?
I can't see anything really revolutionary, at least in the sort of short to medium term. I think that we're just going to see the current evolution continuing here. At least that's what looks like the plans for getting to the large exascale machines that are planned for the US, for example. That's the way they're going to go. However, I think it's good that we're now seeing some more competition in the market, that we're not just stuck with Intel CPUs and NVIDIA GPUs, and that there's more players coming into the HPC market in terms of processors, and I think that'll hopefully drive some of the innovation on a bit faster than it has gone in recent years. So I already mentioned the kind of high bandwidth memory technology. So that's something that I think does have a potential to make a difference to a lot of HPC applications. It'll go at least some way to addressing the imbalance between the compute and memory performance that we have in our current systems. Yeah, I guess I'm still concerned that we don't really, at the moment, have a route to higher performance without just increasing core counts. And I think the effect that that's going to have is that it'll reduce the number of applications that are able to exploit the biggest machines. So I think the target application space for the very largest machines is just going to shrink. Only a certain number of applications will be able to exploit that, partly because of the amount of human programmer investment that's required to get applications to that scale. It's just not going to be feasible to do that for everything. But you can argue whether that's a good thing or not, right? So whether it's, but I think it will be. The largest machines will have a focus on a smaller set of applications. Great.
Thank you very much, Mark, for your input, and it was really nice talking to you. And of course, we wish you all the best for all your current projects. Right, that's it for the episode today. The links for the podcast will be made available on the UK Turbulence Twitter account. You can also go on the UK Turbulence website. It's just UK Turbulence in one word, where you will find all the podcasts that are available on YouTube and on SoundCloud. So thank you very much, Mark, for your time. That was very nice to talk to you.
It's been a pleasure talking to you.
And for everyone listening to this podcast, I hope to see you soon for a new episode.